Good morning, everyone. Welcome to the EasyPower Tuesday Refresher. This is Jim Chastain. I very much appreciate everyone for tuning in today. Hopefully we'll be able to share some information that's useful and productive in using the EasyPower tools. So today we're going to be exploring the options in the PowerFlow module, and I wanted to start real briefly by talking about the kind of the spheres of applications of the different EasyPower tools. Effectively, it falls into two categories. Most of the activity, frankly, short term, has been in worst case system analysis, which includes the modules of short circuit, power protector, and arc flash. And essentially, the focus is on system integrity and being able to survive the worst case that could happen and limit the amount of both equipment damage and personnel hazards, personnel liability. But the same database can be utilized for additional analysis as well, and that falls into normal system operations. And so today we're going to be talking about the techniques and the controls in PowerFlow, which can be used to analyze and optimize system performance, and the same basis, part of the same database, can then be utilized as well for harmonics and dynamic stability. So those are more for future topic, and today I want to talk essentially about basic PowerFlow. Significance is it's probably one of the more complicated analysis tasks, I guess, that you have to deal with in the power systems, and that is because, and ironically, it's the area where the analysis was first developed as far as utilizing computer systems to analyze power systems in terms of the iterative process required. So it turns out the solution is the result of setting up a series of equations that are interactive, and the bottom line is that the power drawn by the loads varies with the voltage varies with the loads, and so you have to go through a series of iterations where you solve the equation coming from both ends of that spectrum, and you hope they meet in the center. Well, it turns out computers are very good at this, and what we end up with is the need in terms of programming the computer for being able to resolve the solution in spite of the fact that there could be differences on where the ultimate solutions of these equations ends up. So part of the controls involves the ability to set the variables involved in this conversions. Specifically, you'll see we have limits on what the delta is in the real power calculations, the reactive power calculations, and then the voltage differences as we go from one bus to the next and solve this series of double-ended equations. We also limit or put a fixed endpoint on the number of iterations that are done, and then how we handle motor starts is also a way to deal with this, the variations in the iteration. And then in addition, we're going to talk about tuning, because that's probably first and foremost the best way to modify what the model is that we use for arc flash analysis or short circuit analysis, because it's more ideal and based upon nameplate data, whereas the PowerFlow will be based upon how the system's actually operating, which may be far different from the total design limits of the equipment involved. So what we're going to be talking about is essentially a systematic approach to convergence, and what you find when you start to do PowerFlow analysis on some systems is that it identifies or can get thrown out of whack because some system elements have been improperly set up. Consequently, the PowerFlow module itself is a good technique or a good debug tool in terms of identifying anomalies in our database initially when we're setting up, when we're doing data collection for a short circuit or arc flash study. Very frequently we'll take power readings, voltage and current readings when there's panel meters available, and then as we get the model developed, run a PowerFlow and see how close the PowerFlow results come to the actual parameters that have been logged, and that in and of itself will help identify system elements that were improperly set up. So the technique of resolving a convergence issue really is fairly simple, and it's a matter of being able to divide the system in roughly half, a dividing point that's roughly half and half, and then following the fault down to the local point where there's an issue. And then we're also going to be looking at the ability to reduce parts of the system and then reduce our calculation time by only running analysis on the section of the system that we've isolated. So there's going to be a couple things going on, and without belaboring it, it's easier just to kind of see how it works rather than talk about it. Now, the ultimate goal then, by making these adjustments, is to be able to identify what the system's power flow parameters are or should be, and that includes bus voltages, generator data, load data, flow, current flow, both real and reactive, transformer taps, branch losses, overloads, and then the detailed reports, which ultimately is what you want to be able to track against your real system. And it's that tracking and that trending that will help you identify areas that need preventive maintenance, elements that could be showing signs of wear or having some issue that should be attended before there's a catastrophic failure, all of which justifies the expense of doing a PowerFlow study or the time invested, because there is a payback more easily identified than you will with just a short circuit analysis. So with all that as kind of the introduction, let me kind of jump into a database in EasyPower. And as we do this, I've introduced a fault in the system or an error in the system. And what I want to do is go into PowerFlow and then solve the equations. And as I do that, it tells me that there is a convergence problem, and to review load summary information, convergence summary report, the buses that have the greatest number of mismatches, and look for equipment errors with excessive loads near that bus. Well, when you have a large system, sometimes that's worthwhile, or sometimes it's a good idea to start there. Here's what the PowerFlow summary report looks like. And even though this is only a 50 bus database, this seems like a little bit overkill in my book as far as trying to do a comparison of mismatches on an individual bus. What I like to do is start off by saying, okay, if I look at my utility, my system's basically divided in two parts. So let's isolate each part. And because I'm in PowerFlow, Smart Breaker allows me to kind of click on the breaker and then isolate the downstream loads. Let's go ahead and solve the equations there. I don't get an error report. Of course, the only thing that's really powered up at this point is my utility and my Clearwater bus. So at that point, I start putting loads back on. And if I double click on this half of the system, all right, so this solved. So chances are pretty good that my problem's on the other side. So as I close this particular breaker, sure enough, I get the indication that I have a problem. And personally, I like to follow the same kind of mentality or progression, and that is, okay, if I follow this load downstream, I'm going to go ahead and open these 3 breakers. I'm going to go back to database edit. After we get a couple rounds of errors, I start to get my PowerFlow faults start to stack up. So I'm going to re-enter, solve the equations, and again, I don't have any errors as long as I have the loads on this bus isolated. Well, if I come down here now and look at what's going on, these are all interconnected. I have 3 winding transformers supplying a series of downstream buses, and they're all potentially interconnected. And so consequently, this is a fairly complex system. You may have noticed when I started off that this breaker was open, and there, just in of it, that's the error that I introduced in my system, is that with this breaker open, I have a fair amount of overload induced that's not necessarily part of my circuit. So again, because that was introduced artificially, I'm going to go ahead and close each of these breakers. Now the point being that this is a breaker that I had open, and so a logical progression would be, if I go back and try to open this again, now with that breaker closed, if my PowerFlow solution now resolves, clearly that was a source of my problems. And as soon as I do that, I can see I have some control warnings that make me realize trying to resolve the problem with that breaker open is not a good idea. So let's talk real briefly about what we're indicating. So I'm going to uncheck most of these boxes and kind of start from scratch here. The first indicator that we have are the voltages. So as we turn on and off the voltages, what we see is the per unit value of the voltage and the voltage angle, current angle, power angle in each of these buses. Now, for what it's worth, if I go to right click and open the PowerFlow options, I can show on the one-line output that I'm either showing per unit, kilovolts, or voltage. So let's, for this remaining session, go ahead and show the voltage, kilovolts. So this I'm showing as a 34 kV, 34.4 kV. And if I go back and look at this, let's kind of go back to my database. So this is 115 kilovolts. This should be 34.5. And the buses down here I'm showing at 12 kV. So when I go back to my PowerFlow and solve the equations, I can see that already I'm losing somewhere close to 80 kilowatts, 70 kilowatts, 70 kilovolts in drop. If I go in and look at my generator outputs or generated data, I can see that each of the generators is performing as it should be. They should be. We can show the load data, and now we're showing the megawatts and the megavars. So this is the real power and the reactive power. If we show in the branch flows, again we're showing the current, and we can show on our PowerFlow options, one line output, branch flows, the kilowatts and kilovars. In this case, let's go ahead and do megawatts and megavars. So the real and reactive current. And what jumps out at you, at least in some of these basic loads, is that I'm drawing almost as much in the reactive power as I am in the real power. So that's an indicator that there may be room for optimization in my particular design. We're going to look at the transformer taps. Now, these are what the transformers are set up at, and this could be an area where we may want to look at things. One of the advantages of the PowerFlow module is it will allow us to set up the automatic load tap changers in a transformer and see where they localize based upon how they're set up. So we'll cover that step in just a second. Likewise, we can see our voltage drops at each of the buses and each of the loads. We can look at the losses in the branch flow, which we're already essentially looking at. We can set controls for the overloads, and these are flagged red. When I go back to so I can address PowerFlow options with this button or with the right click in the center of the screen. And where we modify this or where we control this, in fact, where we control our iteration options are all done under control. So currently we've set up the delta for stopping the convergence at 0.0001 megawatts, which is a pretty small delta, both in megawatts and megavars. And we've also put a limitation of 30 iterations. And so more than likely I'd want to go back and look at my iteration report to find out where we're stopping, but the point is it's solved the equations by the time we get there. It gives us some results. So what I'm looking at right now is the overload threshold. So when I look at my overload report or indication, these numbers are based upon what I've set for, looks like a minus 10% of the rating or 5% of the threshold per unit. And so that's what's generating these indications in red. And then finally, the voltage violations, we're not seeing anything that's giving us a voltage violation just of itself, which is a 10% overload. All right, so then there's some techniques. As I indicated earlier, one of the clear advantages of the EasyPower tools, so here's some overloads down here, is that there are several ways to kind of deal with the system. Part of the problem is that there could be some number of overloads indicated that may not be real because the system doesn't run at the loads, at the rated loads that we're talking about. The tool allows me to select. I can either select individually and then hold down control and select other buses or other loads, or I can left click and drag to select loads. And as I do that, this icon called Scaling Factor Edit opens up, or at least becomes available. And based upon which elements I've selected, I can make adjustments to the constant MVA loads, constant current, and the constant impedance, or I can scale the motors and the motor data and the MCCs. So in this case, we know that our motors run at 40 or somewhere near 45%, and the MCCs run at 55%. So let's go ahead and scale those and see what that happens. The tool says we're going to update 7 items based upon what I've selected. And you can see by making that adjustment, we've eliminated the overloads that were indicated here. We still haven't done anything, or we haven't accomplished our mission, if you will, based upon the control settings and the limits that we're exceeding in this particular leg. If I go back and look at 2 elements that I was talking about earlier, for instance, the load tap setting. This is a 480 volt bus. It looks like we're down to 450. I may have 2 choices. There's a couple choices, but then, so I don't really want to get into the design elements of this, but certainly the tool allows us to do a what-if situation. So let's go back to our database editor. Two solutions might be, or possible solutions might be, add a capacitor to raise the voltage on this particular bus. So let's go ahead and do that. And again, I'm just showing for illustration. I'm not talking about how to design a capacitive filter. I'm going to go ahead and put in a, let's go ahead and put a switch just so we can turn it off and on and see where we get with this. And then while I'm here, I'm going to go in and see what the result of doing a load tap changer, or if for some reason I didn't set up the load tap changer. Let's say we have a sensor that adjusts the two, and the control is on the two sides so that it'll adjust the taps. And now let's go back and go to PowerFlow. It's telling me I obviously have an error, so let's go back and fix the capacitor. And again, I haven't been that careful to look at what the values are, so I'm just going to put in some 400 kV AR and see what that does for me. All right, going back to PowerFlow, solve the equations. Let's go ahead and open this up. Okay, so we noticed a couple things. First of all, we've eliminated our control violation, and what we see is that this voltage has changed only because, or simply because, we put in the load tap changer as part of the transformer. And realistically, that could be improved if we put the taps, based upon while the transformer is set up, if we put the taps on maybe even the supply side. Likewise, when we add a capacitor to this, we actually bring the voltage up greater than what our designated target voltage is, and that's not necessarily a good thing, but it shows the what-if capability of being able to apply solutions in my system. All right, so let's see where else we've gone with this. So now, based upon making some adjustments, let's go ahead and take our capacitor out of the circuit. What I want to do is now look at the reports that we can generate. Let's go ahead and take our transformer back down to no load tap changer and go back to PowerFlow, solve, and look at our, so we've talked about the control options, again, setting up the iteration, the max difference between our solutions. We've talked about the ability to set overload thresholds, voltage threshold, change the display on the one-line diagram. The last thing we're going to touch on are the outputs that we can create, the reports, so we can generate a detailed report with all the bus details, and then summary reports on each of the items. So let's go ahead and do this. And again, as we do that, it reduces the window. It shows these reports down here or under my list of windows. So let's go ahead and show our detailed report. So again, this is for each of the buses, and PowerFlow quite literally is a summation, or the ability to show the flow into a bus and then the flow and losses out of the bus, or actually the flow into and out, and the difference will be the losses. And frequently people will want to minimize the losses, and that's again where you come back to being able to optimize the system and therefore generate cost benefits. And then in addition to this, we're also displaying the PowerFlow summary report, which shows the per unit mismatch for both, this is the mismatch per bus, and then the generator, the load summary, and then the system summary. Transformer tap report, voltage violation report. Again, we want to go in and look at those. Some may be that we still may not have adjusted loads as we should to make them more in line with reality. So there's some amount of, I guess, need to readjust my my load settings in my database, which is what we did initially. And as we walk through the plant and update those settings, we will get more accurate results in terms of the alignment of these outputs with what the readings are we take in the plant, which is another way to go in and set our make our settings, is to measure the current and the voltage, and then identify the source of any of those loads, so that what we're really tracing are the unexpected, if you will, losses, because they will identify the areas of opportunity. All right, so at this point, we've covered all of our outputs. We've covered all of the, I guess, data points I wanted to cover, and we've indicated how we can optimize, or at least the opportunity to analyze voltages, generator data, load data, branch flows, transformers, the drops, the losses, and how to generate reports and make adjustments. So I think that pretty much caps what I was trying to present. And by all means, if you're working on a database or a project that you need some insight or some assistance running the program, by all means contact tech support at easypower.com, and be more than happy to give you an assist to get started on your analysis. Appreciate everyone attending. Have a good rest of your day, and we will talk to you all next week.